this video, we'll talk through the electronic configuration topic from Advanced Higher Chemistry Unit 1. By the end of this video, you should be able to write electronic configurations using spectroscopic and orbital box notations. You should be able to explain the special stability of elements such as chromium and copper, be able to identify which block a particular element belongs to, and also write electronic configurations for different ions. Start off with a reminder of the Ifbow Principle, which gives us the order in which orbitals will be filled. When we're doing our spectroscopic notation, this uses a shorthand to represent the arrangement of electrons. Hydrogen has 1 electron, so it's represented as 1s1. Lithium has 3, which is represented by 1s2, 2s1. And magnesium has 12 electrons, so it'd be 1s2, 2s2, 2p6, 3s2. For some elements that have lots of electrons, it may be more useful to shorten the notation even more. For example, looking at neon and sodium, sodium has 1 extra electron than neon. What we can do is we can represent sodium by putting the symbol for neon in square brackets and just including that last electron, the 3s1 electron. When it comes to orbital box notation, just another way of showing the same thing as the spectroscopic notation. If we're looking at something like oxygen, oxygen has 8 electrons in total. We have 2 in the 1s orbital, 2 in the 2s, and then 4 in the 2p orbital. It can sometimes be represented vertically, where the energy is increasing as you move up the diagram. Most often it would be drawn across the way. Just in terms of space, this is probably how you would see it most often. There are some elements that don't quite fit that pattern. One of these would be chromium, which has 24 electrons. We would expect our last 2 orbitals to be 4s2, then 3d4. However, half-filled and fully filled subshells have an extra stability. They have a special stability associated with them. Therefore, what we actually find is that we have 4s1 and 3d5. This gives us half-filled s orbital and half-filled d orbital. When it comes to copper, which has 29 electrons, we would expect to end with 4s2, 3d9. However, because half-filled and fully filled subshells have extra stability, we actually would get 4s1, 3d10. Types of questions that we could be asked about. Here we just want to know the electronic configuration of vanadium. Vanadium has 23 electrons, and when we start putting them into our orbitals in the correct order, we'll get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3, and that matches our answer of C. Another type of question, we can be asked to write the electronic configuration for a particular element. With this one, I'm going to show you the 2 slightly different versions of it. If it just asks you straight up for the electronic configuration, we are able to use our shorter configurations. If we have strontium, which has 38 electrons, the nearest noble gas is krypton with 36 electrons, so we could represent it as Kr in the square brackets 5s2. If the question says in terms of sp and d orbitals, we would have to write this out fully, showing all the different orbitals involved. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. In this question, we're asked to write the orbital box notation for phosphorus. Phosphorus has 15 electrons. Therefore, we'll have 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, and 3 in the 3p. Next, we're going to look at the different blocks of elements in the periodic table. You can divide them into S, P, D, and F blocks, and this corresponds to the outer electrons within that element. Ones in the S block have their outer electrons in the S, and if they're in the P block, they'll have their outer electrons in the P subshell. When we look at the periodic table, group 1 and group 2 and helium are our S block elements. We have our P block, groups 3 through to 8. Our D block is our transition metals. And our lanthanides and actinides are our F block elements. Questions you could be asked, they can give you a particular element, in this case element number 104. beryllium, which is a transition metal. Therefore, it is a D block element. In this question, we're asked about the noble gases, asked about their outermost orbital. When we look at the full periodic table, this is a question that's trying to trick you. With the exception of helium, the other noble gases are P block elements. However, because helium is a noble gas, our correct answer is D, because it has to have its outermost electrons in an S or a P orbital. Next, we'll look at ionization energies. When we have transition metals, they're going to lose their 4s electrons before the 3d electrons. This is due to the fact that when electrons are present in the d orbital, the 4s orbital is no longer lower in energy. The key takeaway is that electrons are lost from the 4s orbital first. If we have a look at 3 different elements here and look at their comparative ionization energies, this can be explained by looking at electronic configurations. Lithium has a half-filled subshell, beryllium has a filled subshell, whereas boron is not really anything at all. There's the special stability associated with a filled subshell, which means it will be much more difficult to remove electrons from a filled subshell, which is why beryllium has a higher ionization energy than lithium. Type of question could be is just to explain that same sort of idea. This time we're looking at nitrogen and oxygen. If we take a look at the electronic configurations, we can see that nitrogen's P subshell is half filled, which is more stable than the shell in oxygen. This will require more energy to remove that electron. In this question, we're asked about krypton, and we're comparing its electronic configuration to 4 different ions. We count our electrons, we see that krypton has 36 electrons. Our strontium would have 38 electrons, but it's too positive, therefore it's only got 36 electrons. Our selenium has gained 2 electrons to become 2 negative. Again, it's going to equal 36 electrons in the ion. Our arsenic has 36 electrons as well. And our zirconium, therefore, is the correct answer with 37 electrons in its 3+ ion. In this question, we're asked to write an electronic configuration in terms of sp and d orbitals for a nickel ion. Nickel should have 28 electrons, which would be represented as this with 4s2, 3d8 at the end. We need to keep in mind that we're going to lose the 4s electrons first, giving us 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. Hopefully by the end of this video, you're now more confident in writing electronic configurations as spectroscopic or box notations, being able to explain why some elements have a special stability associated with them in terms of half subshells and full subshells, be able to identify which block a particular element belongs to, and also looking at the electronic configurations of different ions. Thank you for watching. Goodbye.